So it's already 2 minutes past the time, so we have some participants already. So let me start. So welcome everybody to this fourth Athena X-ray Advances ASST and ACO science webinars. In this case, we are very pleased to welcome Melanie Habouzit, who is, she received her PhD from the University of Paris 6 under the supervision of Marta Volontieri in 2016. Then she moved on to New York with her first postdoc as a Flatiron Fellow at the Center for Computational Astrophysics. And then in 2019, she moved to her current position at the MPIA Fellow and Galaxies Fellow at the Max Planck Institute for Astronomy and the Center for Astronomy in la Universidad de Heidelberg. Her, as we will see very shortly, her research interests lie in the field of galaxy formation and evolution. Her work includes the connection between central black holes and their host galaxies and their coevolution through cosmic times. She performs her own large-scale cosmological simulations with her model for the formation of massive black holes, and analyzes all the state-of-the-art cosmological simulations for galaxy formation of the field. She's actively working on using these simulations to prepare for future missions, such as Athena, as we will hear in a second. And then without not making anybody wait any longer, please, Melanie, whenever you will.
Yeah, hi, everyone. So thank you for the introduction and for the opportunity to show what we have learned about the AGN population from cosmological simulation. So my talk is going to be very biased to those simulations. So you have a nice example here in the background, which is the Illustris simulation. So those large-scale cosmological simulation, they reproduce a given volume of the universe, and really they allow us to study thousands of galaxies, from low mass galaxy to massive galaxies in different environments, and to also study the black holes and AGN across cosmic time. So what I'm going to show now is from those two papers, so a presentation of all those cosmological simulation and their black holes and AGN, and how we can also use the simulation to help preparing Athena and other future missions, and how those will be really key to maximizing the scientific return of those missions when we can compare the actual observation to the result of the simulations. So I think about a third of this talk is actually new results that are not published yet. So really work in progress. So, if you feel like you can contribute to this, I'm super happy to discuss about it at some point after this talk or later on. Okay, so let's start with what we know about massive black holes. So here's the cartoon showing the redshift as a function of the mass of those massive black holes. And everything below this black curved line is what we know today. So those are all the electromagnetic detection of black holes as of today. So we have the local universe at the bottom, where we really see that, we found massive black holes in very big, large elliptical galaxies, in that case, really massive black holes, but this population of black holes also extend all the way down to low mass galaxies and dwarf galaxies. So here you have a summary of this local population of black holes with the mass of black holes as a function of the total stellar mass of their host galaxies. And we really see that there is a diversity of black holes in the local universe. So again, from massive black holes in massive galaxy all the way down to low mass black hole in low mass galaxies. So this relation that seems to be here between those two quantities that we often call scaling relation is actually telling us that probably there are mechanisms of coevolution between the black holes and their host galaxies. And in other words, if we form a black hole here of 10 to the 4 solar mass at high redshift in a low mass galaxy, is this black hole going to evolve really linearly with the host galaxy? In which case, we will build this relation with this straight line here. Or are actually black hole growing first, and then somehow the galaxies are assembling around the black hole, and this would be this path over there. Or maybe galaxies are actually growing first, and then at some point the black hole is catching up on the growth, and then this would be this path over here. So we really don't know at the moment how we build this scaling relation, and even this diagram that we see in the local universe, or if at all this diagram is actually the same at high redshift. So this is one of the open questions on massive black holes. This diagram is also interesting because we see that we have black holes in low mass galaxies, and those black holes have lower masses than, the biggest black hole. So this is actually telling us, probably it's giving us a constraint on the initial mass of those black holes. So potentially that black holes can form at really, with mass of 10⁵ or even lower. So this is also a key indication and constraint for the population of black holes. So this is everything we know in the local universe. When we go further, we try to observe at higher redshift, we are only able to detect active black holes, the AGN. So this would be, over there is a cartoon. And at the highest redshift, so redshift 6, 7, we observe with the brightest AGN that we call quasars. So those quasars are really extremely luminous objects. So here you see this population of quasars, and they really have bolometric luminosity of 10⁴, 10⁴, so brightest object ever, and they are powered by extremely massive black holes of 10⁸ to 10⁻10 solar mass. So really seeing those extremely massive black holes less than 1 gigayear after the Big Bang, it's really providing us with a key constraint on the formation of black hole. Black holes must have formed very early on in the history of the universe. We've already as massive seeds in order to grow and form the population of quasars. So this is what we know today about massive black holes, if I would be to summarize. So what we can suspect now is that the formation of black hole is basically happening mostly here in this diagram. So we don't know how those black holes form at the moment. We don't have enough constraint, but we have a few ideas. So here I show different mechanisms for the formation of those black holes. So we think that they could even form either form before the first galaxies, in which case, for example, we have the primordial black hole, or they could form within the first galaxies. So for example, it would be the case if black holes form out of the remnant of the first generation of stars, the POP2 stars, in which case you see that black holes would have, the seeds of the black holes would have mass of 100 solar mass, for example. But they could also form at the center of nuclear stellar clusters, and that would be these mechanisms, or they could also form in atomic cooling yellow under very specific condition. And in that case, they form actually really massive seed of 10⁴, 10⁵, and even more solar mass. So we have this diversity of theoretical model today, but we are not able yet to say if one of them is actually correct or if it's a combination of those different mechanisms that explain this diversity of black hole that we see today. So those mechanisms, they need to explain the diversity of black hole. The channels are also not mutually exclusive. It could be a combination of those different mechanisms. And each mechanism determine the initial mass of the black holes, but also their abundance in the universe. And this is important to explain, again, the detection of black holes today. So each mechanisms have advantages and caveats. So for example, just to give a few examples, if black holes form out of this first generation of stars, we will expect to have black holes in all galaxies, more or less, because we have the first stars in many galaxies. But they may be actually too light to sink efficiently in the center of their host galaxy and to grow efficiently to actually, for example, produce a high redshift quasars. So this is their caveat that they form with lower masses. On the other hand, this mechanism is very appealing because we form massive black holes, but some work have shown that they could be rare black holes, so that we wouldn't explain that we find a black hole in all the galaxies in the local universe, for example. So at the moment, it's really not clear how we form those black holes. Once formed, they will grow mostly by accreting the gas from their surrounding and by merging with other black holes, so along those lines, for example. So today we really need to understand both the formation of black holes, but also how they evolve through cosmic time. And Athena will be actually key to do this. So we will really, so this is the parameter space of Athena. So Athena will see the active black hole, and we will really target black holes that have lower masses, but also at higher redshift than what is possible today. So you see here that we nicely extend our limit, like the current limit that we have today with observation. At the same time, we will have the LISA mission. So here we detect merging black holes, so not the active one, but the merging one with a gravitational wave emission. And you see that it will nicely complement Athena. So those two missions will really target lower mass black holes and higher redshift black holes. Okay, so today obviously I will focus on Athena, but I think it's nice to see that it will be very complementary to LISA. Okay, so now to understand, how those black holes evolve and how galaxy formation evolution is actually happening, we need to capture a large number of highly nonlinear processes. And to do this, cosmological hydro simulation are a really good tool. We can, I think, can show the movie here. We can really resolve thousands of galaxies. So you see here, large-scale filaments, dark matter halos, and in their center, galaxies are forming. Eventually, you will see the impact of AGN feedback. So now you can see the bubbles here that are really AGN feedback able to impact their host galaxies and their surrounding, large-scale surrounding here. So really, those simulations are key today to understand black hole and AGN evolution through cosmic time. So the simulation, we have a few of them in the field of galaxy formation. So I listed some of them here, and there are two others that I will show at the end of the talk. So Illustris TNG, that is the next generation of Illustris. So there are two different boxes, Horizon-AGN, Eagle, and SIMBA. So the simulation, they really capture a given volume of the universe and really resolve galaxy with stellar mass of 10 to the 9 all the way to 10 to the 11, 10 to the 12 solar masses in different environments. So the spatial resolution of the simulation is about 1 kiloparsec, and the size of the simulation is between 100 co-moving megaparsec to 300 co-moving megaparsec. So really fairly large volume of the universe, and they were run from high redshift all the way down to the local universe at redshift 0. So of course, with the simulation, we don't resolve everything. So we have to rely on what we call subgrid physics to capture bionic processes happening at very small scales, so below the galactic scales. And this would be the case for star formation, the way we model supernova feedback, and the physics of black hole. So the physics of black holes is divided in three categories. So the first one is black hole formation. So in all the simulation, the formation of black holes is actually not modeled as a function of theoretical mechanisms, the one that I've shown before. So instead, black holes are formed in all resolved galaxies so that we ensure that there is a black hole in all the galaxies. And all the black holes start with a fixed initial mass for most of the simulation. So it could be 10 to the 4 solar mass, or 10 to the 5, or 10 to the 6, for example, for the new TNG simulation. So all black holes start with the same mass. And then black holes can accrete gas, and this is modeled by via the Bondi formalism. So all the simulations are the same in spirit, but they use different modeling. So in this case, for example, for gas accretion, it's more or less everywhere the Bondi formalisms, but there are variations for each simulation. And black holes can also grow in mass by merging with other black holes. And finally, if black holes are active and accrete gas, they can also inject a fraction of this energy into their surrounding, and this energy will couple to the gas and impact the host galaxy and the larger scale surroundings of the black hole. So this is what we call AGN feedback, and it's really important to actually get the properties of the galaxy right in the simulation. So this was kind of a summary of what the simulation are doing. So what we get from the simulation for the black holes is the mass of each black hole, of all black holes at any time, and also the accretion rate, so that we can derive, what would be the bolometric luminosity of those black holes, and what is the luminosity, for example, in a hard X-ray band, or any band that you want to work with. There are two things that are really important to remember. The first one is that AGN obscuration is not something that is done on the fly in the simulation. We cannot do that. So you can always correct for obscuration, but it has to be done post-processing. And because we don't know much about obscuration at high redshift, it's one of the biggest unknown when we try to compare simulation and current observations. The second thing is that those simulations, although they have a nice resolution, they do not resolve short timescale variability for the AGN. So this is also something that we can correct for in a post-processing fashion. Okay, so those simulations, they were really made to study and understand galaxy formation and evolution. So I have to say that they, at first order, they are doing a very good job at producing galaxies that look like observed galaxies. So for example, in terms of the star forming main sequence, but also the diversity of morphology that is produced by the simulation. Sizes are also getting better and better with those new simulations. And the fraction of quiescent massive galaxies is also, fairly good in the simulation. So, for galaxy at first order, this was the goal of the simulation. They do a good job. One question that I had for a long time is whether those simulations are actually able to produce black holes in agreement with observation. Because often we focus on the galaxy properties and not that much on the black holes one. So we, a couple of years ago, we started a big project of comparing all the black hole population in the simulation to understand if they were in good agreement with observations. So I'm going to present this now. So the first thing that we can look at is the relation between black hole mass and the stellar mass of their host galaxies. So you will see a lot of figures like this that are very busy, but it's because each panel is for one simulation, so we can compare them. So here we're looking at the local universe, so redshift 0. So the simulation are in colors, and the observation are within this cartoon shape that is really made to be a cartoon. So what we can see is at first sight, there is a good agreement between simulation and observations. Simulation are within the observational plane. But when we look carefully, there are tighter relation in simulation than in the observation at fixed stellar mass. So for example, here we are missing, and it's true for all the simulation, different level, we are missing the Horizon-AGN, for example, that we see in the local universe. Oops. We are also seeing missing the most massive black holes at fixed stellar mass. That would be this region over there. And some simulation, because of their seeding, are actually producing two massive black holes in no mass galaxies. So for example, in TNG, the initial mass of 10 to the 6 solar mass for the black holes is producing this population of black holes here that is way too massive compared to the observation that we see in dwarf local galaxies. So there are discrepancy between observation and simulation, but also among the simulation. So we wanted to understand this in detail. So what we did is to we followed in time all the Illustris and TNG black holes and galaxies. So those two simulations was very smart of the different team to actually use the same initial condition for those two simulations, so that you start from the same density perturbation, so that you will really form the same galaxies in Illustris and in Illustris TNG, so that you can match galaxies. And because the physics of those two simulations is different, you can actually see the impact of the different physics on the black hole and galaxy coevolution. And this is very nice to learn a lot about the physics. So here it's again the black hole mass as a function of the galaxy stellar mass. So just to guide the eyes, observation are now in gray. And we're following, two matched black holes and galaxy, one in TNG, one in Illustris. And this is what is shown by those two lines here. So in Illustris, black holes start with a mass of 10 to the 5 solar mass. So this is the dot here. But in TNG, they start with 1 order of magnitude more massive seeds. So we start from 10 to the 6 here. And while the Illustris black holes is able to accrete in the low mass galaxy, you see that in TNG there is this plateau, and this is due to the modeling of supernova feedback. The modeling is stronger in TNG, so that the black hole is not able to accrete gas, so you have this plateau. While in Illustris, it's a weaker supernova feedback, so the black holes can actually accrete with those galaxies. And you see that this is also changing the AGN activity, and this is shown by the color of the line. So black holes can be more or less active depending on the physics of the simulation. So supernova feedback is one example, but you see that all the way we have differences across those two black holes. So just to illustrate this impact of supernova feedback, I'm showing now two zoom-in simulation, high-resolution zoom-in simulation of Yuan Dubois. So this is one low-mass galaxy before a supernova event at high redshift, and this is after the supernova event. So it's a bit dramatic here, but basically a supernova event, if you model it with a strong feedback, it's able to destroy the cold gas reservoir of the black hole, so that the black hole is not able to accrete. And this will lead to this shape here, that you have a plateau, and then the black hole eventually can accrete when the galaxy is large enough to overcome the supernova feedback. If you're employing a weaker supernova feedback, your impact, the supernova event is impacting the galaxy, but it's not destroying the cold gas reservoir. So the black holes can actually accrete and evolve linearly with those galaxies. So Willy supernova feedback is able to change the coevolution of the black holes and their host galaxies. And this will be important in the following of the talk. So this was for the black hole properties. Now, what if we move to the AGN population? So we were wondering if the AGN produced by the simulation are actually in good agreement with the current observations. So one thing that is interesting to understand is that there is no calibration of the simulation on AGN properties. So everything that is related to AGN properties is actually a true prediction of the simulations for all of them. So I like to show the number density of AGN. So again, it's a very busy plot, but I will walk you through it. So we're looking at the simulation in colors. The shaded area is a combination of observational constraints from those three papers. So we are first looking, and we're looking at this as a function of redshift. So first we're looking at relatively faint AGN with Hardix-Way luminosity between 10⁻42 and 10⁻43 ergs per second. And what we see is that a simulation like Eagle is doing a good job at reproducing the observational constraint. But some simulations are overproducing this number of faint AGN quite strongly, for example, for Illustris TNG or Horizon-AGN. When we move to slightly brighter AGN, we see that the simulation that was doing a good job previously is now, overestimating the number of those AGN at high redshift, underestimating them at low redshift, and some simulation also obviously still show some disagreement. When we look at the brightest AGN, we also find some discrepancy. So for example, here we don't have any of those AGN, although we observe some of them in the low redshift universe, and this is also the case for Illustris and Illustris TNG. So the takeaway message of this very busy plot is that first, all simulations produce different population of AGN. That's the first thing. Second thing is that all the simulations have actually a hard time reproducing both the faint and bright AGN, but also the low redshift and high redshift AGN at the same time. So most simulations are able to produce one of the regimes, but not all of them at the same time. And this was actually interesting to see. So this was for when we consider all AGN in galaxies with stellar mass above 10⁻⁹ and higher, so literally 10⁻⁹ to 10⁻11, 10⁻12, depending on the simulations. Now, if we're only considering galaxies of 10⁻10 and higher, this is what we find. So the conclusions are still the same, but the level of agreement is slightly better. So this suggests that we have too many AGN in low mass galaxies with stellar mass of 10⁻⁹, 10⁻10 in the simulation. So probably that some of the simulation really model the feedback from supernovae, like they model supernova feedback with a lower strength than what could happen in the universe. So a 2-week supernova feedback. Of course, this can be combined with the accretion properties of the black hole. So maybe black holes are not able to accrete that much independently of supernova feedback, or this could also be due to the initial mass of black holes, so it's degenerate things. Okay, so to show you a bit more of the disagreements, discrepancy between observations and simulations. Now I'm looking at low mass galaxies, and we're comparing, so this is the work of one of my students. So she's comparing the fraction of AGN in those low mass galaxies. So basically simulation are here and here for different luminosity of the AGN, and we're comparing this with current observational constraint in the local universe. So of course there is kind of some uncertainty in the observational constraint because it's hard to detect AGN black holes, in dwarf galaxies because they are less massive, so fainter AGN. But what the student was finding is that some simulation seems to have way too many AGN in those low mass galaxies. So again, it can be 2-week supernova feedback. For some simulations, it's actually too massive black holes in those low mass galaxies. So this is really interesting to understand what the simulation are not able to reproduce at the moment, because when we predict what the future mission will see, we have to keep this in mind. So this was for local low mass galaxies. Now, if we're moving to massive low redshift galaxies, we can also look at the fraction of AGN. So this is all galaxies with stellar mass above 10 to the 11 solar mass. So we're really looking at the massive galaxies in the simulation and in observations. So observations are shown with the black cross. So at high redshift, we have a fair amount of those galaxies that still have an AGN at high redshift. And then there is this drop, and the fraction of AGN in massive galaxies oscillating between 20% to 40%. So this is for the observation. Simulation in colored shaded areas are reproducing this trend. So we have more AGN at high redshift than we have at low redshift. So this is, so far so good. But when we look carefully at what's happening below redshift 2, some simulation really do not have any AGN in those massive galaxies. And this is maybe due to a too strong AGN feedback. So we employ AGN feedback in the simulation to reduce the star formation rate of those massive galaxies, to produce this population of quiescent, quenched galaxies at low redshifts. But doing so, we also quench the AGNs themselves a bit too much in some simulation. So this also can affect the population of AGN. Okay, so this was an overview of how the different simulation compared and what is different from observation. So we do find discrepancy between the black hole population and the AGN population. But on the other hand, when we compare all the state-of-the-art simulation, when we take them all together, it really allows us to capture the uncertainties on the modeling of the simulation. So for example, supernova feedback, AGN feedback, the seeding of the simulation, we can really assess the impact of those choices in the simulation and how they impact the properties of the AGN and AGN prediction. So this is way better when we take all the simulation rather than just taking one simulation. And this will be very important, for example, for Athena, both to prepare the mission, understand how many detection we could have according to the simulation, but also to maximize the scientific return of the mission. So this is what I'm going to describe now. Okay, so this part, yeah, from now on, it's basically figures that I've done recently. So, if you want to help doing this and trying to see what Athena will be able to see, you can always talk to me later. So this is showing the sensitivity curves of past and current X-ray surveys. And we have the Athena surveys here. So I took surveys that were described already in the literature. So a deep survey for Athena here with a high sensitivity. It could be an area of 5 square degrees on the sky, and then a wider survey of 50 square degrees, but with a slightly lower sensitivity here. So I took those 2 surveys, but of course, everything that I will show can be done for any kind of sensitivity curve. So that's also the power of working with cosmological simulation. So with those simulation, we can answer 3 key questions. The first one is, how much of the AGN luminosity function distribution we can cover with Athena? How deep we can see in the AGN population? The second question is, what population of black hole will power the AGN that Athena will discover? And the third question is, in which galaxy will those AGN that Athena will see are located, and how we can, what we can actually learn with the Athena detections. So those are the 3 questions that we can answer. Okay, so now I'm showing the X-ray luminosity function of the AGN in hard X-ray. So it's again very busy. So we're looking at redshift 0, and then we're going all the way up to redshift 7. So in gray, we have several observational constraints. So at low redshift, they kind of agree. And then when we go to higher redshift, they start to, of course, because we don't have that much constraint, they start to show some discrepancy. And it's the same for simulation. So in colors now, we have redshift 0. So the simulation, you see that there is some discrepancy, but overall, let's say that they more or less agree. And then when we are moving to higher redshifts, discrepancies start to increase. So you can see here that between the simulation Eagle that has a relatively faint AGN population and the simulation like Illustris TNG that has a very bright AGN population. There is more than one order of magnitude discrepancy in the luminosity function. And this discrepancy between some simulation stays all the way to high redshift. So you can see here with the hours. So now if we overlap with what Athena will see, so I'm showing this with so the dark shaded area are what Athena will not see. So it's a mix between the deep and the wide survey here, just cartoonish to explain. So Athena will not see this part, but Athena will see the right part over there. So basically Athena will have the resolution, enough resolution, and sensitivity to actually distinguish between what is predicted by cosmological simulation. So we will have enough detection and power to actually distinguish between, like a simulation like TNG and like ASST and a simulation like Eagle or Blue Tide. So this is great news. I think Athena will observe a significant fraction of the AGN population at any redshift, including high redshift, and this will be good to understand the AGN population. Okay, so when we look at the detection now, so this is just a quick visualization of the TNG 300 simulation. So it's one of the largest simulation the largest simulation that was run all the way down to redshift 0. So here I'm only showing redshift 5 to redshift 10. So all the white dots, gray white dots, are galaxies or black holes in the simulation, and the blue dots are the black holes, the AGN that Athena could see. So here it's actually misleading. This is a full volume here of the simulation that is collapsed into a map. So blue here has a detection at redshift 7, and here you have the same at redshift 6, where of course as we go to lower redshift we have more and more AGN that can be detectable. So this is what we can really go to high redshift with Athena. So now to look a bit more, quantify this a little bit further, this is the number of detection per 100 co-moving megaparsec cube for all those simulation. So you see again that the discrepancy that we were finding in the X-ray luminosity function, it's translating here in the number of detection. So the discrepancy is large enough that when we have the data from Athena, we will be able to disentangle the cosmological simulation. So Athena will be very powerful in doing so. So this is an example for number of detection for what could be the wide field and a deep survey for Athena. Yeah, so I put some number here just to think about. So basically at redshift 8, according to those simulations, we could detect from 0 to 6 AGN per 100 co-moving megaparsec cube in the simulation. At redshift 7, from 1 to 25, 30 AGN, and at redshift 6, from basically 10 to 100 detection. So you see that really the discrepancy is so large that Athena will be really useful to disentangle the simulation and potentially their modeling. Okay, so this was one aspect that we're reassuring that Athena will be super useful. Now we want to understand that what black hole population is actually powering the possible detection with Athena. So I'm showing here the X-ray luminosity of all the AGN in the simulated volume of the simulation as a function of redshift. And here we're showing all the simulation. So the two sensitivity curves of a deep survey and a wide survey of Athena are shown here with the line. So everything that is above the line can be detected by Athena. So what we see with the color code of the dot, that is the mass of the black hole, is that Athena will be sensitive to black holes more massive than 10 to the 6 solar mass for the deep survey and 10 to the 6.5 and higher for the wide survey. But we will miss the newly formed black hole that have a mass of 10 to the 5, for example. So this would be, this tail here that we see at high redshift. So we will miss those black holes, but that's okay because really going to black hole mass of 10 to the 6 and higher it's already learning a lot about the black hole population. When you stare a long time at this figure, you can also find discrepancy between the simulations. So for example, Illustris, you have this cell here that is below the detection limit of Athena, but a simulation like SIMBA, you see that the tail is actually within the detection region of Athena. So you find discrepancy between the simulation. So to quantify this a little bit further, we can look at the black hole mass distribution. So here at redshift 6 and at redshift 3 for all the simulation. So again, Athena will see black holes of 10 to the 6 and higher. So basically at high redshift, we will target, we will find black holes of 10 to the 6 to 10 to the 7 solar mass. For most of the simulations, so you said it's the case for Illustris, for the TNGs, for the ASST simulation, but simulation, according to some simulation, we will also see black holes of lower mass than 10 to the 6. So for example, Eagle have some black holes below 10 to the 6 solar mass, and the SIMBA simulation also start at 10 to the 5. So depending on the simulation, we would see different population of black holes. And then at redshift 3, this distribution is basically getting larger because black holes are, of course, evolving in mass. So we can also see black holes that are more massive when we go to lower redshift. So there are differences in the black hole population that Athena will see. Okay, so this was for the properties of the black hole. So now when we look at the galaxy host properties, so in which galaxies are we going to find the AGN that Athena will see? So this is showing, again, the detections in 100 co-moving megaparsec cube volume, and we're going from redshift 3 all the way to redshift, for example, 8 here. And each line is one given simulation. So the first thing to notice is, of course, again, the discrepancy between the simulation. That is good because when we have the observation, we can disentangle the simulation and their modeling. But one thing to notice is that for most of the simulation, there is this peak at all redshift, basically. So this is telling us that Athena will mostly detect AGN located in galaxy with a total stellar mass of order 10 to the 10 solar mass at basically all redshift and for most of the simulation. So this is the first thing to notice. What is interesting to see as well is the low mass galaxy regime. So basically what is below this 9.5 solar mass here. So you see that some simulation really have a large number of detection in those galaxies. So this is the case for the Illustris simulation, but also to some extent for the for the TNG 100 simulation. So this is because if there is an inefficient supernova feedback modeling in the simulation, the supernova feedback is not able to quench the black holes or to regulate the accretion in those low mass galaxies so that you will power more AGN. So in that case, it will really lead to a large number of detection in those low mass galaxies. The number is so large that, you know, of course, with Athena, just Athena, we will not have the stellar mass of those galaxies, but this, you know, this large number here will also appear in the raw detection number, independently of the stellar mass here. On the other end, if we have an efficient supernova feedback, a strong supernova feedback, or for example, a weaker black hole accretion in some cases, you know, we will have less detection here. So when you look at the amplitude of this, you know, the difference between those two types of simulation here, it's so large that you will see it on the raw number of detection with Athena. So we can really start to disentangle the modeling of the simulation. So for example, supernova feedback or strong is a powerful, no, it's not the word, like how a black hole can actually, the ability of a black hole to accrete gas or not, that is also slightly different in the simulation. So Athena will constrain a combination of black hole galaxy physics. So again, black hole formation efficiency. So whether we have black holes in those galaxies, accretion, so whether black holes are able to accrete gas efficiently or not, and also the role of the feedback. So supernova feedback, but also AGN feedback, all those processes. So this is, I think, given the discrepancy between the simulation, I think this is really one key thing for Athena that we can disentangle the simulations. Okay, so now moving on the detection power of Athena. So I don't know if this is actually a thing or not, but I call detection power this. So basically the number of agents that are detectable by Athena divided by the number of galaxies in a given stellar mass bin. So basically this is telling us that for a given stellar mass, in a stellar mass bin, whether we can see all the galaxies through their AGN or not. I don't know if it's clear, I hope so. So basically this is what this figure is showing for different redshifts. So what we see first is that there is a large, first of all, the detection power according to the simulation is different. So it varies from one simulation to another, but there are some similarities. So for example, if we look at TNG, the TNG simulation, for galaxy of 10 to the 10 and higher, there is a high detection power, meaning that with Athena, and I think this is a deep, the sensitivity of the deep survey, but we can do it for any survey. We will basically be able to see almost all galaxies in a stellar mass bin of 10 to the 10 solar mass. So because those galaxies have AGN, we will be able to see them through the eyes of Athena. At higher redshift, it depends on at higher stellar mass, it depends on the redshift. So at higher redshift, we will see those galaxies with their AGN. At lower redshift, because AGN feedback is quenching the galaxies and also the AGN, we will have sometimes in some simulation a lower power of detection with Athena. So you know that this large detection power of 10 to the 10 and higher solar mass is actually true for most of the simulations, except Eagle. So Eagle has a very faint AGN population. So AGN are so faint that they tend to lie below the detection level of Athena, so that the detection power will actually be lower. So we would, in a given stellar mass bin, we will miss, up to 40% of the galaxy, for example, here. Yeah. So of course, this is without considering the obscuration of AGN. So on top of this, those optimistic results that we will see all the galaxy of 10 to the 10 solar mass and higher, we have to consider obscuration of the AGN. That could also depend on the stellar mass of the host galaxies, the luminosity of the AGN. So this is also something that we have to work on. Okay, and I think this is my last couple of slides. So just to show you what regions of the black hole mass stellar mass relation we will actually see with Athena. So of course, we only see the AGN. We cannot measure the black hole mass of the stellar mass, but we could also use a combination of other surveys to do so. But in any case, just to show you where Athena lie in this diagram. So this is redshift 7, so different simulations. And the line is the Cormendi et al. Scaling relation here, just to guide the eye. So blue dots are the black holes in the simulation. The green dots are the black holes that we could see with a very high sensitivity, such as Athena Deep Survey. And the cross are what we could see with a wide survey with Athena. So you see that at redshift 7, depending on the simulation, I mean, more or less all the simulation, we will see black holes above 10 to the 6.5. So this is basically what is above here for more or less all the simulation. We see that in some simulation, we are really not able to capture the black holes that are strongly regulated by supernova feedback. So that's the case here for the ACO simulation. But overall, we capture kind of a nice area of the diagram. So when we move to lower redshift, we can see more and more AGN. So again, we are above 10 to the 6 in terms of the black hole mass. But again, we capture, almost, a fair amount of a fair fraction of the diagram. And redshift 5, we will also see the entire thing. So again, we are like some area, depending on the strength of some physical processes happening, we will not see, for example, here's a black hole that are, if supernova feedback is efficient in regulating black hole growth in dwarf galaxy, we will not see those detection with Athena. Okay, so this led me to my conclusion. So large-scale cosmological hydro simulation are really good to study black holes and AGN through cosmic time, and also black holes interact with their host galaxy or they co-evolve. Definitely, from those two papers, we've learned that the simulations of the field, they produce different populations of black holes and AGN, not always in good agreement with observations. But on the other hand, when we looked at all those simulations all together, we can actually really assess the uncertainties on the black hole and galaxy physics that we used in those simulations. And this is very useful to prepare the upcoming missions, but also it would be useful to maximize our scientific returns, because when we get the observation, we can go back to the simulation and try to disentangle them on their modeling. So for Athena, I've shown you that Athena will observe a significant fraction of the simulated AGN populations in all simulations, so this is good. Mostly Athena will see black holes more massive than 10 to the 6, 10 to the 6.5 solar mass. In galaxy, mostly of mass 10 to the 10 and higher. We will miss the least massive black holes, the newly formed black holes, or the ones that are not accreting, but that's okay. And we will also, Athena will detect AGN in dwarf galaxy or low mass galaxy of 10 to the 9, 10 to the 10 solar mass, if, for example, supernova feedback is relatively inefficient. So comparing observation and simulation, we can disentangle those different physical processes. And if we manage to link this to a galaxy survey, for example, we can also get a good understanding of the coevolution between black holes and galaxies. So yeah, I will stop here. Thank you for your attention.
Okay, thank you, Melanie. Very nice talk. It's always nice to see people that understand the simulations explaining to people less familiar. So it's very, very nice. Thank you. So it's now the time for questions. I see one hand raised. Paul, please go ahead.
Hi, Melanie. Yes, very nice talk indeed. As you pointed out, one of the big uncertainties is the obscured population, and so then we have problems with both the unobscured population and the obscured population. So in the unobscured population, it's very hard for us to determine, especially at higher luminosity, the stellar mass. On the other hand, we can do that for the obscured population, but then it's much harder to determine the black hole mass. So are there any, from the simulations, are there any hints of proxies or other observables or other properties that we might be able to use to search for in the data to help with this?
Yeah, so the obscuration is always an issue. So for the simulation, you can always add, post-processing a model to capture for the obscuration, but it's so, it carries so big uncertainty that, you have to try several models. What some simulation have been doing is to look at the column density around the black hole. Although with those simulation of 1 kiloparsec, I'm not sure that this is actually, it's not the highest resolution possible, right? So it's also carries uncertainties. Yeah, to me, the easiest thing is to try different modeling post-processing, but it's true that it remains one of the big unknown also in simulation, as it is difficult, especially when you compare to observations, because yeah, it's a nightmare. Yeah, I don't think there's any proxy. Yeah, if you only see the luminosity of the AGN, I mean, you have to look for the column density, and you can try to kind of compare with simulation, but I don't think it's very accurate from the simulation side.
Yeah, I mean, we also have some hints that the obscured population might evolve differently to the unobscured. So we're looking to you really to the simulations to try and understand. Of course, if you put it in post hoc, then then that's hard to do. But to trying to understand that is it would be nice to connect the simulations and the observations in that respect. But yeah, I'm not quite sure how we do that.
No. I mean, I think it hasn't been done yet. Obviously, because it's one of the hardest thing to do. Yeah, I think we also get into a resolution issue to do this, but yeah, I agree that it's definitely something to look at more carefully.
Okay, thanks. Anyway, it was a good talk.
Okay, thanks, Paul. Any other questions? There seems to be a new one. Okay, Massimo, please.
Hi, thank you for the nice talk indeed, and very interesting. A curiosity concerning the AGN feedback. What is is there a consensus among you theorists? I mean, when you use the input parameters for the AGN feedback, do you always use, or better, I would ask, do you always need the so-called ultra-fast outflows to have the AGN feedback effective, or you may not need it? Or what is a general? Is there a general rule that you are using there?
Yeah. So also, yeah. So
outflows.
Yeah, that's also very interesting. So also simulation. So we believe that we need AGN feedback first of all to quench galaxies and the massive galaxies. So they all rely, also simulation, they rely on an AGN feedback to do this job of quenching galaxies, but they all use different recipes. So at high redshift, it's often injection of thermal energy, what we could call the quasar mode, and at lower redshift for black hole with a lower accretion rate, there is a really diversity of modeling. So some simulation use also a thermal feedback, so they don't distinguish between quasar mode and radio mode, so that the eagle simulation. Some simulation used more like a release of kinetic energy to model an outflow. That could be bimodal or more or less collimated outflow. So they really all use different things. So I think at lower redshift in more massive galaxy, it's more like a kinetic feedback. But there is really no consensus at the moment. And also the strength of the feedback is different. So for example, the new TNG simulation, they improved the feedback. So now they produce a really nice population of galaxies. Also the quiescent population of galaxies, the population of quiescent massive galaxies also better than the previous simulation. But on the other hand, their population of black holes is now really strongly regulated, a bit too much. So there is also this issue that we were looking too much at the galaxy properties to work on the AGN feedback. So we were only, I'm picturing here, but we were only looking at the galaxy properties, and we discover now that we also need to get the black hole right and the AGN population right. So it's work in progress. But no, there is no consensus. Although simulation use different recipe for their modeling of AGN feedback. Yeah.
Okay, thank you.
Thank you, Massimo. Any other questions? I'm checking the attendees, panelists, and Slack. Okay. So I do have a question or a curiosity. Oh, Matteo. So please go ahead.
Yeah, Melanie, thank you. It's an excellent talk, very interesting, but also somewhat concerning, isn't it? Because you are showing us that when you compare the simulations with the existing AGN population at redshift lower than 3, none of them is able to, let's say, reproduce accurately the AGN population in the whole luminosity and redshift range.
Yeah.
So, when you then try to imagine how to use this simulation to maximize the outcome of a future mission like Athena, you don't want to be in 15 years time in the same situation where the data remains undecided as far as the models are concerned. So my question to you is there a specific redshift regime or luminosity regime which carries the strongest diagnostic power among models, that is the one on which we should focus our attention when we design future observations, in order to minimize the risk that entropy will dominate it in 15 years' time as well?
Yeah, that's a very good question. So yeah, it's difficult because most of the simulation, they actually, like all of them, they're able to reproduce a given regime of the agent. So some simulation really produce a faint agent very well and like in good agreement with current constraint from low redshift to redshift 4 or 3, 4. But on the other hand, they do not produce the bright agent. So it's like there is no one simulation that is able to produce all the regime in a nice way. So they all have those discrepancy, which are very complementary. So I guess if we look carefully, we could maybe find a regime with less uncertainty, as you said, that could be useful to actually focus on that and try to disentangle. Yeah, I haven't think about this this way, but yeah, it would be interesting to look more carefully at this. To me, if I see some discrepancy in the simulation, I'm actually happy because then I know that if we get more observational constraint, we can go back to the simulation and see how what was done in the wrong way. So if we observe too many detection with Athena, we know that we have to go back to the simulation, and maybe some simulation produce too many agents in low mass galaxies. So I'm thinking the other way around. But I think, yeah, I don't know if it would be possible to find a luminosity regime that they all tend to agree on. Yeah, probably relatively bright AGN is a regime with less. Yeah, if we go to the luminosity function. Yeah, I mean, you see it's a lot of discrepancy, but yeah, at high redshift.
Well, we don't need to answer in the next 30 seconds, but that's something, that's the kind of perspective that probably we need also to inject when we try to demonstrate the best way to use Athena to solve this issue. Where is really the diagnostic power that we want to look at?
Yeah, to me, I look at, if I see discrepancy, it's actually good, but it's true that then you have to also think in terms of observations. But okay. Yeah, I agree.
Yeah, thank you anyway. Very, very nice talk, Melanie. Thank you.
Okay, any other questions? Don't see any in the panelists or the attendees. We're getting into the hour now, anyway. So Matteo has still his hand up. Do you have another question, Matteo, or is it? Okay, thank you. Okay, no Slack either, I think. No. Well, I had a curiosity. I mean, in one of the last few slides, there was like
this maybe, or the black hole.
There, that one. Okay, so and in the TNG 100, so this is the detection power as a function of mass for different redshifts, and I see that the redshift 2 is it 2? Yes.
Yeah.
In TNG 100, there is a deep. Yeah, that one.
Yeah, exactly. Yeah. So in this simulation, there is. So basically, before, like for lower mass galaxies, we're in this quasar mode of the agent feedback that is not that efficient in regulating the galaxies and the agent, and then we are transitioning really here into this kinetic mode of TNG that is very efficient in quenching galaxies. So this drop here is actually due to the kinetic mode of the agent feedback that is regulating both the star formation in galaxies, but also the agent in those galaxies. So basically, it's the agent population in those galaxies way fainter, so that you wouldn't be able to detect those agents with Athena. So it's causing this drop here. So
the radio AGN are happen to be around that mass. Okay.
Exactly. Yeah.
It's nice to know somebody who understands this.
Yeah, exactly. So this simulation is doing a good job for the properties of the galaxies. Yeah. So, but depending if agent feedback is happening at what redshift and which stellar mass, we could also disentangle this maybe with Athena. So it's also one thing we could do.
Okay, thank you. So any other questions? I don't see anything. So unless there is any last moment questions, we just thank Melanie again for a very nice talk and explain all these things to us and helping us understand what Athena can do for astronomy in the future. And thank you all the participants for their presence and their questions. So see you next time.
Thanks, everyone.